Hey everyone, welcome back. Ever notice how some AI art generators spit out the same face over and over, like they're stuck in a loop? Or why a text model might repeat the same phrases? It's like the AI is stuck in a rut, unable to explore the full range of creativity. Today we're diving into why this happens, and how researchers are fixing it. So let's start with the basics. Imagine you're teaching a robot to draw pictures. You show it thousands of cat photos, and it learns to create new ones. But here's the catch. Sometimes the robot forgets how to use the rules it learned. This is called posterior collapse in AI models like Variational Autoencoders, VAEs. Think of it like a painter who only uses one color because they forgot how to mix paints. The model isn't leveraging the full range of possibilities in its internal, latent space. That's the abstract map of features the AI uses to generate data. Why does this happen? Well, VAEs work by encoding data into this latent space and then decoding it back. But if the model gets confused about how the latent space connects to the real data, it just skips the creative part and copies the input directly. It's like a chef who relies on a single recipe instead of experimenting with spices. Traditional fixes tried to force the model to use the latent space by adding strict rules, but these rules were architecture-specific. They only worked for certain models. That's like telling every chef to use the same kitchen tools, even if they're not the best fit. Enter the new solution, Latent Reconstruction, LR loss. Instead of rigid rules, this approach focuses on something simpler, local behavior. Imagine checking if a recipe's ingredients are balanced in every bite, not just the whole dish. The LR loss doesn't care about the model's structure. It just pushes the VAE to reconstruct both the original data and the latent variables. It's like teaching a student to solve problems with multiple methods, not just one formula. The results? Wildly impressive. Researchers tested this on datasets from simple digits, like MNIST, to high-res faces like FFHQ. The VAEs generated diverse outputs, even when the latent space changed by the tiniest amounts. It's like a chef who can tweak a recipe's spices just right, creating entirely new flavors every time. So what's the big deal? This isn't just a tweak, it's a shift in how we think about AI. By focusing on flexibility and local behavior, we're making models more adaptable. No more one-size-fits-all rules. Just smarter, more creative AI that can handle the messy, real-world data we throw at it. But here's the deeper technical kicker. This solution hinges on a mathematical principle called local inverse Lipschitz continuity. Think of it like a map. If 2 points are far apart on the map, in the hidden space, their real-world versions should also be far apart. If not, the map becomes useless, like a GPS that can't tell the difference between your house and the grocery store. Mathematically, this means the decoder's output has to scale with the input distances, multiplied by a special factor called L. If this breaks, the model can't distinguish between different inputs, leading to chaos. The encoder's job is equally critical. It has to ensure similar real-world inputs don't end up in the same spot on the map. If 2 different photos start overlapping in the hidden space, the model gets confused, like a librarian who can't tell apart 2 different books. This is where loss functions step in. There are 2 main ones. 1. Data reconstruction loss, LDR. This measures how well the decoder can recreate the original input. If the output is blurry or wrong, LDR screams, "Hey, fix this." 2. Latent reconstruction loss, LLR. This ensures the encoder's hidden representations stay true to the decoder's expectations. If the encoder starts cheating by squishing different inputs into the same spot, LLR acts as a watchdog. Together, these losses create a feedback loop that keeps the latent space structured and the model creative. It's the difference between a painter who sticks to one palette and one who dynamically adapts their colors to the scene. Thanks for watching. If you're curious about how this applies to your favorite AI tools, drop a comment below. And if you want more deep dives into the science behind the tech, hit that subscribe button. Until next time, stay curious.